Enhanced redundancy of ST2059, now by now you know the abbreviation, time transfer over ST2022-7. Who knows what that is? Cool, cool. I like all these abbreviations. Redundant networks. Thomas Kernan is a software architect at Mellanox. His main area of work is focusing on defining network architectures for the media and entertainment market. Is anybody here who does not know Thomas? So why the hell do I read this thing? Thomas, you have the floor.
Thank you, Hans. So yes, I was wondering how many SMPTE standards I could actually put into a title. I only cut it down to 2 of them. And this is the short version, Enhanced PTP Redundancy. So the reason this presentation was put together by myself and Nick Kirol, who's my partner in crime on many of the PTP presentations we've done in the past, is about we're now at a stage where people are deploying PTP and we want to build these all IP studios. What is it that we actually need to do in order to make sure that the designs where we have redundancy not only from a media point of view, but also from a timing point of view can actually happen? And there are different ways of doing this. So the whole point here is to explain what is it that you don't know yet and should be looking for, and what is it that is already available, and again, why is PTP not that scary after all? So the IP Studio, obviously we've got Essence Transport that's converging. Obviously, you've already heard about all of these standards, it being 2022-6 or TR03 or AES67 or 2110. All these are different means for carrying the essence, not a problem. We had, as previously mentioned by Paul, systems which were based around Blackburst, tri-level sync, or other means to carry that type of information. We came up with this model where we want a converged network to only have only one cable for all the different parts of the essence and the system, including control, intercom, and whatever else may be in the mix. So why not add sync onto this too? There's obviously the basic precepts of what we're trying to build here. From a time transfer point of view, and again, Paul's explained a lot of this in detail, so I won't cover it more than is needed. We have frequency transfer with SDI. We've got relative phase transfer through black and burst, tri-level sync. We have in an IP system an asynchronous medium, obviously, as it's been explained. We've got PTP 1588. We can carry the phase, the absolute time, and, well, the frequency, the absolute time, about phase, we can have a discussion. 1588, as Paul has also mentioned, is an IEEE standard. We're working on version 2, also known as 2008. Some of you are aware there's an upcoming revision that will happen most likely sometime next year at this point in time because it's not been completed. It is backward compatible with version 2, so the sky's not falling. You don't have to worry. These are extensions to the existing standard. We can reach sub-microsecond precision. By the way, we can actually reach sub-nanosecond precision in very well-engineered networks. I was actually attending the ISPCS, which is the main IEEE 1588 conference a few weeks ago. And if you want a projection in the future where PTP actually needs to go, they're talking about tens of picoseconds. Okay, completely different scale in terms of time and accuracy they need. So we are not the ones who have the strictest timing requirements in the industry. Widely used, as it's been explained, it being in telecom, in power, in finance, test and measurement, industrial automation, and others. The whole point of 1588 is highly generic. And this is very important because it has allowed all these different industries to take the same common framework and to customize it via the PTP profiles, the ones that are relevant for this industry, obviously 2059 and the AES67. A brief 101 on PTP, just to get everybody on the same page in case there are some reasons where you need a quick refresh. It's a simple hierarchical model. We have the Grandmaster, of course, that is being selected. We're going to discuss in a little more details what is important about a Grandmaster selection in redundant networks, obviously. It's a two-way time transfer model. The clock deviation is calculated and corrected, and it's done on a per message basis. So obviously you are continuously calculating and correcting. This is something that also can be perceived originally as a little scary because when you look at your PTP logs, you see that it's moving around all the time, but this is normal. This is the natural way the PTP operates, but it moves around in the nanosecond range. if it's well implemented. It uses the best master clock algorithm, and in order to reach sub-microsecond accuracy, timestamping, hardware-based timestamping at the network card PHY, it being an FPGA based or it being a regular NIC base, is required. There are operating systems which don't support hardware timestamping right now, Windows specifically. Linux, it's not a problem, although the next revisions of Windows do introduce PTP, by the way, but it's still software-based timestamping. So, you know, we've still got some time to go before there is a common understanding on how to do that on the Windows platform. That doesn't mean that there aren't people that are implementing it properly under Windows with hardware. You just need to get the right hardware. Beware of transmission delays. We're talking about IP networks. Packet delay variation is one of your enemies in this case. Okay, so transmission delays, 1588 was designed about having a symmetrical network path. Any asymmetries that are introduced, especially those that are variable in nature, will impact the timing precision. So the network design has to take that into account. So the quick animation of PTP messaging, you have a master which is sending a sync message to all the slaves. This can be done usually using multicast, in some cases using unicast. In the broadcast industry, it depends on the profile, it depends on definitions. Both are allowed. You have therefore two timestamps, T1 at the master and T2 when the slave has received it. And then there is a delay request that is issued by the slave towards the master. Okay, so every single slave will send that back up to the master. In default implementations, this is done over multicast, but since it's only to be addressed to the master itself, you can also do it over unicast. It's supported in 1588 in the 2059 profile. This reduces a bit of the noise on the network, which is a good thing for some implementations. And then once the master has received the message, it will do a delay response telling the slave when the master received the message. Now you have 4 timestamps, and with those 4 timestamps, you can actually draw your offset and your delay. Those are the 4 timestamps you need, nothing else. This is the 101 of PTP, but this is PTP in a nutshell. What's important in terms of PTP is the election process. So it's based on announced messages and their timeouts. In order to have a coherent infrastructure, everybody needs to have the same values dialed in to all the devices. If you have some devices that are working with different values, you may have a system where the slave thinks it's timed out because it's not using the same announce and timeout values as other parts. This has actually come across in real-world implementations, so I always tell people the first thing to do is double-check if you have the same announce and timeout messages. The messages contain information about the clock quality. So is it locked to a specific reference? Is it locked to, as in a GPS? Is it unlocked from GPS? Is it locked to another kind of reference? This is the basis of what you use for the BMCA, the election. In case the master, there is no master, either during startup or due to a failure, the nodes will all compare their announce capabilities. Okay, so the clock properties are reviewed, and they will all converge to select one and only one master, i.e. the Grandmaster. Okay, that's where the terminology Grandmaster comes from. So that's one case. The other case is I am upgrading my infrastructure. I am introducing a new master into the infrastructure. So after an upgrade, typically. So first thing you do, you listen to the messages on the network. Who's the current Grandmaster? What are they announcing in terms of properties? If your clock properties are better, you start announcing yourself. That issues yet another BMCA. But the current Grandmaster will understand that somebody is better and will therefore back off, and the new one will become the Grandmaster. That's how we work also with redundancy. Because if I have 2 that have the same values, there is always a tiebreaker. That tiebreaker is used to determine who's the current Grandmaster, and all the other ones that are candidate Grandmasters, or passive masters as we also refer to them, will be waiting their turn in order they need to come online on the network. 101 on network design, you usually have one of 2 choices. Either you're doing a spine leaf type of architecture with one spine or multiple spines and a whole set of leaves, or otherwise you're doing a hub and spoke model. Depends on the size of the network, depends on the architecture. But ultimately, you're moving essence over IP between switches. Your endpoints will be in a spine leaf architecture, most likely connected to leaves. Why? Because the ports on the spine are usually 100 gig or 400 gig, or let's say there is a high cost or penalty for carrying traffic directly into the spine. Obviously, if it's a hub and spoke, everything is directly connected. It's a different consideration. These are based around design requirements, but it's going to be one or the other. When we're coming to redundancy, the 2022-7 redundancy model, we obviously want redundancy from an essence point of view. So as you can see here, we've got a red and blue network, or amber and blue network, A and B network, depending on how you wish to label it. In this case, I've built it with two different spines and a set of leaves connected. Your endpoints are on the leaves. You've got sources such as a camera, or you've got a receiver such as a multi-viewer. Due to -7, due to the fact that we want the redundancy with two separate paths, we're receiving traffic over those two paths. So the source is sending out across the two fabrics, and then the receiver is receiving across the two fabrics. And -7 being well known by most people, it is using the RTP sequence number and just drops the duplicate packets received. So everybody's sending everything, everybody's receiving everything, and the receiver itself decides to dedupe and drop the duplicate packets. So that model works fine for essence. Now, the industry wants to find a model equivalent for PTP redundancy, and this is where the interesting part of the talk starts. So what's redundancy from a PTP point of view in an all-IP studio? Again, we've got the exact same two fabrics. We've got the exact same two senders and receivers from a media point of view. In our case, they are PTP timed and slaved off Grandmasters. I said before, there is only one active Grandmaster at any point in time. In this topology, it actually has two connections, one onto each of the two fabrics. So we're using the same time source. And then we have the passive masters, which are doing the exact same thing. So in my case, I never put two Grandmasters, I always put three, because there is an N+1 redundancy model, and why stop at two? Three is useful because if you've got two of them and one of them is lying, you don't know which one of the two is lying. So having a third one in the room can be quite useful. That's a whole discussion on its own. The point here is the PTP traffic is going to both networks. The slaves would theoretically be receiving PTP messages on both interfaces. Now, what happens in this case, and this is where it becomes interesting, because the IEEE 1588 specification doesn't tell you what to do in these topologies. Other industries have addressed it with very specific designs. In the power industry, they've gone and built an entire specification just around redundancy topologies. And we're now at this phase in these environments of what is it that needs to be done for PTP redundancy. So what's the impact here? As I was explaining on the previous slide, we use a sequence number for the -7, very basic. It's the same essence, it's the same packet, that's not a problem. With -2 or 2059-2, PTP supports limited redundancy via BMCA. You understood that the only thing that triggers a BMCA is the announce or lack of announce messages, i.e. timeout or it hasn't been received. So whilst we take into account the quality of the time source, so that's the attributes that define if it's a GPS logged or if it's free running or one of the other modes are in there. There's a whole table of clock classes and clock qualities they used. The time transfer itself is not taken into account. If you've got packet delay variation between the two paths, if you've got a longer path, if you've got optical electrical converters which are introducing some additional delay on one of the two paths, if you have maybe even different firmware versions, all these things can contribute to having differences in timing between those two paths. So from a PTP error condition point of view, what happens here? You got a Grandmaster failure, it's pretty straightforward. You select a new Grandmaster through the announce and properties of the clocks. You have a loss of external reference, so you were GPS locked. You have now degraded your clock class. Another passive master can be elected to take over. These are all scenarios well understood. There are no issues here. When we start missing event messages, this is where the interesting stuff starts. So we're in a situation where the slave has got to do something about it. He's most likely going to start free running in one way or another. You've got corrupt messages due to an error condition on the 5, for example. Same thing. How do we, as a slave, support this? Is the message complete? Is the message incomplete? What's happening here? I have incorrect timing information. All these need to be taken into account. Back to the packet delay variation. I have unreliable timing information. Remember, we're talking about symmetrical designs. 1588 says that basically you have a symmetrical path. If you start having asymmetries in here, and it's not the same on path A and path B on top of everything else, how do we handle it? So, we built a measurement setup. We decided to throw a bit of equipment at it, and this is what it looks like. We had two Grandmasters. We had both off the same GNSS signal. In this case, it's GPS locked, so I didn't do GPS versus Galileo or versus GLONASS or any other system. I took GPS in both cases. Two Grandmasters, they're totally independent. They're connected, each one to each fabric, okay? So we're trying to isolate here to explain what happens. We were using two different network card implementations here that support PTP and hardware, a dual port NIC, and a reference NIC. The reference NIC is here to make sure that we understand if the data that we're getting is skewed in one way or another on the main NIC, which is the dual port NIC, which we're using to connect to both fabrics. All of these are wired back to via 1 PPS to the scope. So what we're actually measuring, or what we will be measuring in the next slides, is we're using the 1 PPS of the Grandmaster as the actual reference, okay? That is the reference point on the scope, and then we are comparing the 1 PPS output of both of those NICs in terms of how the PTP stack has represented the time between when the master and when the slave has received it, so the whole PTP stack operation, and then the output of the 1 PPS port. So we want to measure outside the PTP domain to understand if there are any absolute end-to-end differences between the two paths, and it's down to implementation or not. So first things we did is we made sure the Grandmasters ran stable for 30 minutes. Frankly, they were up and running for more like days anyway, but we decided that whenever we would start a test, we wanted to make sure that at least 30 minutes were locked and everything was proper. We're using boundary clocks. In the first test that I'll show you, we're actually using the same identical models for the network switches. Then we decided to make things a little more interesting and use the two different models, because some people are designing networks intentionally with different hardware, because in terms of redundancy or in terms of possible issues, and we want to explain to you what happens if you do that, or what could possibly happen. We're using 2059-2 default rates in terms of announced messages and syncs. And the measurements were basically done once we had locked and stable slaves. So we waited out more than 5 seconds. We waited out a few minutes just to say we want to make sure everything is purely and fully stable. We're measuring the 1 PPS out, as I mentioned, and we're cross-referencing with the 1 PPS from the Grandmaster. So, results. This first graph will be from the dual port NIC that you saw connected purely to the blue fabric. Okay, so we had the red and blue fabric. So the measurement you see here is the two different ones from the reference one, that is actually the one that is closer to the 0 axis, and then the other one that is around 400 nanoseconds offset, which is the actual dual port fabric. There's the details, of course, in the paper itself. Obviously, you see that this is a measurement that was done over a certain period of time, which is why you see it slightly moving. This is normal because this is how PTP operates. Remember, every single time you actually have an operation with those 4 messages and the fact that you have 8 messages per second, you are basically drawing a new result, and therefore there's always a slight variation. This should not worry you in any way. This is absolutely normal in terms of how PTP and how a 1 PPS signal is generated out of the PTP. What's going to be interesting is what you see now on the next slide, which is when I actually do the exact same graph, but on the red fabric. So there was only a very, very slight shift. Okay, it can be down to rounding, and it can be down to various little, let's say, finite tuning in how PTP operates, and that is a whole different discussion. But for the purpose of the presentation, ultimately, there is no difference right now with those two representations. Obviously, and we're going to discuss afterwards, why is it that there is a difference between the two network cards? This, on the other hand, as you see, there is a jump. This is using a different switch model. okay? So on the previous slide, with one switch, you saw that I had more of an offset than with another switch. So somewhere along the path in the boundary clock implementation that was being used, due to software, firmware, any other reasons, there was a change, okay? But on the other hand, it appears to only impact more one than the other in terms of the two NICs. So is it down to the NIC? Is it down to how the one PPS is generated by that NIC? Is it down to a firmware issue on the NIC itself that's measuring it? These are all things that need to be taken into account when you're actually trying to characterize the information you're looking for. So the other view, of course, is if you don't have one PPS out, and not every device has, is you want to look at it from the offset seen from the PTP stack. So this is from the blue fabric, and then this is overlaid with the red fabric. They actually don't see any difference between one or another from a pure PTP point of view. So one of the assumptions is that the way the one PPS is generated obviously gives us a better view because it's a full end-to-end out-of-band representation. But on the other hand, the fact that we were seeing that larger offset appears to mean that the vendor who provided the dual port, in that case for that specific measurement, has some sort of feature or compensation that is missing for that 400 nanosecond offset compared to the other vendor. That's why we're using multiple vendors in terms of switches and in terms of NICs. Another thing that comes up a lot in discussions is around redundant Grandmasters, okay? So I'm often questions about why is it that we would allow to have more than one Grandmaster at the same time. You might have two fabrics that are disconnected, you know, they're too far from one another, or for whatever reason you decide you want two Grandmasters that are operating in parallel. From a redundancy point of view, this makes sense, okay? But there's usually a concern. So this is a diagram of a 4-day test of two separate Grandmasters, okay? Two different implementations, two different antennas, two different cabling sets, to demonstrate that the actual offset between those two Grandmasters over a 4-day period is obviously well in the limits of a 1 microsecond defined in 2059, and more to the point, if you look at it here, it's more around a 40 nanosecond offset, okay, between the two of them, which is not something that is contributing significantly to any offset within the 2059 design of a plant. So you can have more than one active Grandmaster operating. For example, in those two fabrics, they might not be fed from the same Grandmaster because of distances or design. So you can actually have those operating. So it's not a problem of having redundant Grandmasters that are operating individually. So what is it we need to do in order to provide an enhanced PTP synchronization model? Okay, we can have multiple time feeds that are providing to the different PTP slaves. We can build redundant networks, as we obviously know. We can have multiple active Grandmasters, as I explained from the previous slide. If they are connected on the same fabric, you might want to do this over unicast. It has drawbacks, of course, in terms of messages and the fact that we usually want to use multicast in order to scale better. Or you want to use different PTP domains. These are different ways of doing it, okay? So you could have one port on the NIC listening to one domain and the other port listening to another. The other thing you're going to come up with is you're going to have multiple PTP instances. So not a single stack, but maybe two stacks, one for each of the two ports, okay? So the basics of how the PTP is operating, the stack itself, is going to be the same. But what's going to change, and this is the important part, I'd say, is the fact that you've got to have a selection criteria about the quality of that information. That is outside of the 1588 standard per se. Okay, it doesn't define how you've got to do that. You have, of course, availability, you have quality, those are the basics for the BMCA, but what you don't have is the third point, the statistical analysis, where you want a weighing voting algorithm in there to decide, well, at what point in time, beyond the fact that they are both absolutely identical and from the same reference clock and are using the same clock properties, at what point in time do I determine that I move from one of these sources to the others being the one I'm going to work against? And that's where the interesting work actually starts. That being said, all of this, and this is the good news, is PTP compliant. Okay? There is nothing in here that is being discussed that is not PTP compliant. So, my conclusions. I know Hans is on his way, so I'm good on time. So, -7 is a great model for Essence because you're replicating the exact same media in those packets and you're just tossing duplicates, but it's not a functional approach for PTP itself. Not all paths are equal, as I explained, and as you saw from the measurements. Okay? Whilst we had a very simple network design, we saw differences in how these networks were being designed in terms of either the NICs that were being used as slaves or the boundary clock implementations, and that was causing issues. Obviously, there are also operational changes that may occur in the network that could impact this. BMC alone, as you understand, is not sufficient for exploiting the full requirements for redundant networks. It only looks at announced messages, so it's a simplistic view of building redundancy. You can totally use multiple Grandmasters because they are from a traceable source, GPS, GNSS. And by the way, version 2.1, the upcoming revision of standards, supports multiple parallel Grandmasters. It is part of the upcoming spec. So the extensions will allow you to do what we were talking about previously in the slides. What is important is adjusting the dynamic variations of the time feeds, and here it's where the enhanced selection algorithms in the PTP stack, which, as I said, is outside of what is defined in 1588 and is part of the special source of every PTP stack, will take over, and that's the important part. So, thank you for your attention, and hope this was useful for you, and open to questions.
Thank you, Thomas. Here we go. Questions to Thomas? Meryl? No? Andy? Andy?
Thank you for showing the graph of the 1 pulse per second result and the mismatch.
Yep.
I couldn't read the fine print. Did you say that was a 40-second slew or a 400?
400 nanosecond.
Okay. Nice, big, wide, beat on with hammer, maybe. Firmware error in NIC card?
So one of the NICs had an implementation which you saw is around 15, 20 nanos, the offset, but that's the end-to-end offset, so that's what we were expecting. The other one, and we're now tracing it back with the vendor to a firmware bug, we assume, in the way they actually do the rise of the signal for the 1 PPS, and there's an offset in there. So those 400 nanoseconds were useful to identify there was an issue with an implementation, but we believe that is actually a false, it's incorrectly implemented, and it's going to be fixed in the future firmware revision.
Thanks.
One question from my side, actually would have been to both Paul and your side. Now, from the user perspective, is it going to be cheaper than previous synchronization schemes or not? Or do you simply say there's no alternative?
Well, first of all, I think there is no practical alternative. And the second thing I think is that once you get to a point where we're building all these off-the-shelf systems and that the designs of the network cards that we're using are good enough, and not every card is equal, of course, the benefits of having the converged network and infrastructure combined with what was being discussed earlier, virtualization and all the rest, will ultimately bring it to a cost model which is effective. I don't know if it's going to be cheaper, frankly, Hans, but I believe it'll be, from the flexibility and what we can do, we're going to have more benefits than drawbacks.
So I think conclusion is you can't escape. So become yourself familiar with the technology as soon as possible. Thank you. Thank you, Thomas.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.